Imagination is more important than knowledge. Einstein said that. And he meant it. Because knowledge tells you what is. Imagination shows you what could be, what must be. When Einstein looked at gravity, he didn't just see what everyone else saw. He imagined something completely different, something nobody had dared to imagine before. You're standing right now. Feel the floor beneath your feet. What's happening? You say gravity is pulling you down. Earth's mass attracting your mass. A force reaching up from the planet's core, grabbing you, holding you. That's what Newton taught. That's what everyone believes. But Einstein asked a different question. Not, what is gravity? But what if everything we think we know about gravity is backwards? This is how revolutions begin, not with answers, with better questions. Stand up. Drop your keys. They fall. Simple. Obvious. You've seen this a million times. But have you really seen it? Einstein would say no. You've looked, but you haven't seen. There's a difference. Looking is passive. Seeing requires imagination. Seeing requires you to question everything you think is obvious. The keys fall to the floor. Everyone says Earth pulls them. But Einstein saw something else. He saw the keys finally free. Free to move naturally. Free to follow their true path through reality. And that path happens to point toward Earth's center, not because anything pulls them, but because space itself, the very fabric of reality, is curved. This sounds insane. Space is empty, isn't it? How can emptiness be curved? But that's the limitation of common sense. Common sense is built from everyday experience, and everyday experience is limited. Einstein understood this. He said common sense is the collection of prejudices acquired by age 18. See the truth, you must be willing to abandon common sense. You must be willing to imagine the impossible. Here's what Einstein imagined. He imagined he was in an elevator, a closed box with no windows. He feels weight. His feet press against the floor. Normal. But here's the question. Is the elevator sitting still on Earth, or is it in deep space, accelerating upward at exactly 9.8 meters per second squared? Can you tell the difference? Drop something. It falls to the floor in both cases. Jump up. You come back down in both cases. Stand on a scale. Same reading in both cases. There is absolutely no experiment, no measurement, no observation that can tell you which situation you're in. Gravity on Earth or acceleration in space feel identical, not similar, identical. Most people would say, that's interesting, and move on. Einstein said, if they're indistinguishable, maybe they're the same thing. This is the equivalence principle, and from this one insight, everything changes. Think about what this means. If gravity and acceleration are truly equivalent, then what we call sitting still in a gravitational field might actually be a form of acceleration. You, standing on Earth right now, might be accelerating, constantly, every second, accelerating upward even though you're not moving. This seems impossible, but Einstein had the courage to follow the logic wherever it led. If sitting in gravity is the same as accelerating, then what about falling? An object falling freely feels weightless. Astronauts in orbit float. They feel nothing. No gravity, no weight, no force. They feel exactly like they would floating in empty space, far from any planet or star. But Earth's gravity at the altitude of the space station is still about 90% as strong as on the surface. So why don't astronauts feel it? Einstein's answer is radical. They don't feel it because no force is acting on them. Falling is the natural state. Falling is what happens when no forces interfere. The astronauts aren't defying gravity, they're surrendering to it completely. And paradoxically, surrendering to gravity feels exactly like escaping it. This is Einstein's revolution. Objects in freefall have no force acting on them. None. Zero. The apple falling from the tree, the moon orbiting Earth, satellites circling the planet, astronauts floating in their capsule. All of them experience zero force. They're moving naturally, following their natural paths through reality. But how can falling be natural motion? Doesn't falling require a force pulling downward? Only if you assume space is flat. Only if you assume reality is what it appears to be. Einstein dared to imagine otherwise. What if space itself is curved? What if massive objects like Earth don't pull on other objects but instead warp the very geometry of space around them? Bend it, curve it, create valleys and hills in the fabric of reality itself. If space is curved, then what looks like a curved path to us might actually be the straightest possible path through that curved geometry. Imagine an ant walking on a sphere. The ant thinks it's walking in a perfectly straight line. But to you, watching from outside, the ant is clearly following a curve. The ant isn't wrong. From its perspective, on that curved surface, it is going straight. That's what's happening with everything near Earth. We're all moving through curved space. We think we're being pulled, but we're actually following straight lines through curved geometry. This is Einstein's profound insight. Gravity is not a force between objects. Gravity is the curvature of space-time itself. Notice I said space-time, not just space, because Einstein realized something even more radical. Space and time are not separate. They're woven together into a single fabric, a four-dimensional fabric where past, present, and future coexist, where distance and duration are different aspects of the same thing. Massive objects create wells in this space-time fabric. Depressions, curves. The sun creates a deep well. Earth creates a smaller one. Even you, sitting there reading this, create a tiny well, too small to measure easily. But it's there. Your mass warps space-time around you ever so slightly. Objects moving near these wells naturally follow the curves, not because anything pulls them, because they're following the straightest possible paths through curved geometry. This is what we call geodesics, the shortest path between 2 points. On a flat surface, a geodesic is a straight line. On a curved surface, a geodesic curves. The moon orbits Earth because it's following a geodesic through the curved space-time around Earth. In that curved geometry, the straightest path is a circle. The moon isn't being held in orbit by some mysterious force. The moon is doing what comes naturally, following the geometry. An apple falls from a tree for the same reason. The branch was pushing it upward, preventing it from following its natural path. When the branch breaks, the push stops. The apple is suddenly free to follow the curve of space-time near Earth's surface. And in that curved geometry, straight ahead through time, points toward Earth's center. You, standing on the ground right now, are not in a natural state. The ground is pushing you upward, preventing you from following your natural path. That's what you feel as weight. Not gravity pulling down, the ground pushing up. You're like someone in an accelerating rocket. The floor pushes against your feet. You feel weight, not from any mysterious downward force, from being accelerated away from your natural path through curved space-time. This is Einstein's revolution. Falling is natural. Standing still requires a force. Everything we thought we understood was backwards. Einstein didn't discover this through advanced mathematics first. He discovered it through imagination, through thought experiments, through daring to question what everyone assumed was obvious. He said that if he couldn't explain his theory to a 6-year-old, he didn't truly understand it himself, because truth is simple, not easy. Simple. The hard part is seeing past all the assumptions we've built up. Once you understand gravity as geometry, extreme phenomena make sense. A black hole isn't a place where gravity is incredibly strong. A black hole is a place where space-time is curved so sharply that all geodesics, all possible paths, lead inward. Even light, traveling at the ultimate speed limit of the universe, following the straightest possible path, cannot escape. Not because something pulls it back. Because every direction it could go, forward or backward or sideways, curves inward. Space-time itself has folded into an inescapable trap. We've detected black holes. We've photographed their shadows. We've observed gravitational waves, ripples in space-time itself, created when black holes collide and merge. Einstein predicted these waves in 1916. We detected them in 2015. A century later, his imagination showed him what was real before technology could confirm it. This is the power of thought. This is what Einstein understood. The universe doesn't reveal itself through observation alone. You must think, you must imagine, you must dare to question everything. Einstein said the most incomprehensible thing about the universe is that it is comprehensible. We can understand it. But only if we're willing to abandon our preconceptions, only if we're willing to see what's really there instead of what we expect to see. Newton's equations still work for practical purposes. We use them to launch satellites, calculate orbits, predict eclipses. They're simpler than Einstein's field equations and accurate enough for everyday applications. Newton wasn't wrong. He was incomplete. He described what happens. Einstein explained why. And this is crucial. Science doesn't progress by proving previous scientists wrong. Science progresses by asking deeper questions. Newton asked, how do objects move under gravity? Einstein asked, what is gravity? Different questions lead to different answers. Deeper answers. More beautiful answers. Beauty matters. Einstein insisted on this. The universe operates on mathematical principles of profound elegance. E equals mc squared. The most famous equation in science. 5 symbols. Connecting energy, mass, and the speed of light. Revealing that matter and energy are interchangeable. That a tiny amount of mass contains enormous energy. Simple, elegant, true. His field equations for general relativity are more complex, but they have the same elegance. Mass tells spacetime how to curve. Curved spacetime tells mass how to move. Simple principle, profound consequences. From this one idea, everything follows. Planetary orbits, tides. The precession of Mercury's orbit, a tiny effect Newton's theory couldn't explain, but Einstein's predicts perfectly. Gravitational lensing, time dilation, black holes, gravitational waves, the expansion of the universe itself, all from geometry, all from daring to imagine that space is not what it seems, that time is not absolute. That reality is far stranger and more beautiful than common sense suggests. When you step on a scale tomorrow, you won't be measuring how hard Earth pulls you. You'll be measuring how hard the scale must push to prevent you from following your natural path through curved spacetime. When you watch something fall, you won't be seeing gravity in action. You'll be seeing an object finally free to follow the geometry of reality. When you look at the moon, you won't be seeing an object held in orbit by force. You'll be seeing an object following the straightest possible path through the space around Earth. A path that appears circular, because space itself curves. This is Einstein's gift, not just new equations, a new way of seeing, a new way of thinking. He showed us that imagination and curiosity can reveal truths that mere observation never could. He showed us that questioning the obvious is not foolish, it's essential. He showed us that the universe rewards courage, the courage to imagine what seems impossible. Mass curves, space-time. Objects follow the curves. That's gravity, not a force. Geometry, pure geometry, and that is far more beautiful than any mysterious pull could ever be.